So as we get started thinking about resistance and resistivity, I'm going to ask you a series of thought experiment questions, and I would like you to keep in mind that the analogy between electric current flow and fluid flow is an extremely tight one. So with that, let's start by imagining that I have two wires that are made of the same material. They're both the same length. We'll say that length is L. But the upper wire is fatter than the lower wire. So which one of these has the greater resistance? The upper one or the lower one? Pause and get back with me. So yeah, the lower one here has the greater resistance. Just like it's harder to get water to go through a skinny pipe than a fat pipe, the same is true for pushing charges through a wire. It's harder to push charges through a skinny wire than it is a fat wire. All right. Let's take another one here. So here I'm going to look at two wires that both have the same cross-sectional area. But the second wire is shorter than the first wire. So again, which of these wires is going to have greater resistance? Pause and get back with me. So yeah, the longer one's going to have the greater resistance. We know from experience it's harder to run water through a long pipe than a short pipe. And here it's the same kind of deal. The electrons, as they travel through, will have more partially shielded nuclei to collide with. So you're going to have greater resistance. Okay, let's do one more. So here, let's imagine that I have two wires that have the same cross-sectional area and the same length. In fact, to make that point blatant, I am just going to copy and paste. There we go. There's my two wires. Now the difference is that this quote-unquote wire is actually some ceramic. Actually, let's just make it plastic. And not any kind of funky, weird plastic, just plastic. And this is copper. So which of these has the greater resistance? Pause and get back with me. So yeah, of course, the plastic will have the greater resistance. It's a lot harder to push electrons through plastic, so much so that plastics get used as insulating material. All right, so if we put all that together, we realize that what the resistance of something is going to depend on is the material, the length, and the cross-sectional area. So actually, let's do that. So you can say that the resistance is equal to the resistivity times L over A. So this is a lowercase Greek rho. It's the same one that you used for density. Yes, we are recycling symbols. You make it the same way, and you still have to fight the desperate urge to turn it into a tadpole. All right. So this quantity rho here gets called the resistivity. And if we think about the units we need this to be, we need, after I divide length by area and times it by resistivity, I need to end up with ohms. So there aren't any ohms here at all, so I'm going to need an ohms. This is going to be meters squared over meters, so this is just going to be meters. Meters over meters squared, so this is going to be 1 over meters. And so if I'm timesing 1 over meters by this to get ohms, this better be ohm meters. Now, a lot of tables will quote resistivities, but depending on your application, sometimes what people will be concerned with instead of resistivity is what's called conductivity. So conductivity turns out to be the reciprocal of resistivity. This is a lowercase Greek letter sigma. And you just draw it like that. Don't draw it like a cursive O, because then it looks like a cursive O. Okie dokie. So either tables will quote conductivities or resistivities. The units of resistivity are inverse ohm, inverse meters. Now, here's where it gets really annoying. In a lot of engineering application, this inverse ohm, I kid you not, gets called a mho, because ohm backwards, get it? Ha ha. Yeah, I'm laughing on the inside too. But anyway, they do that. And some of them even take it one step further and actually write it as an uppercase omega upside down. So if they do it like this, they will often write this as something like mhos per meter or some such thing like that. That's just a thing that you'll run across in a lot of engineering tables. But I would write it as inverse ohm, inverse meter, and feel a lot better about myself in the process. So just to make this concrete, let's think about the wire in a toaster. So if you ever take a look at a toaster, you'll notice that there is a very long wire that zigzags back and forth inside the toaster. And what happens when you pop the toast down is you throw a switch that causes an electric current to flow through this very long wire. So the wire that often one of the alloys of wire that often gets used is what's called nichrome wire. And this is a nickel chromium alloy. And if you look it up in the tables, I mean, it'll depend on the exact alloy you choose, but a good typical value for the resistivity of nichrome is about 1.5 times 10 to the negative 6 ohm meters. Now, if you look at this, you'll realize that if you follow the zigzags of the wire in your toaster, there's an awful lot of it there. So probably not 10 meters worth, but hey, that makes the numbers clean, and it is a lot. And typically the diameter of our nichrome wire is going to be on the order of, let's say, 1/10 of a millimeter. So then the question is what is the resistance of our chunk of nichrome wire? If you want, go ahead, pause the video and try to work it out for yourself first, and then get back with me and we'll see what we get. Okay, so the resistance is going to be the resistivity times the length over the cross-sectional area. So this will be the length over the area, which is pi d squared over 4. Or if you want, you can divide this by 2 and use pi r squared. I don't really care. So this is going to be 4 rho L over pi d squared. All right, so this will be 4 times 1.5 times 10 to the minus 6 ohm meters times our 10 meters of wire over pi times 0.0001, because it's 1/10 of a millimeter, meters squared. Grind that all through, you get about 1910 ohms, which seems like a perfectly respectable value. Okay, some stuff that I want to mention, but I'm not going to spend an awful lot of time on, either just because it's not going to be a huge focus or because we'll be doing much more with it later. I do want to get just a little bit more into the microscopics of current flow here. So we will look at current density. So if I have a chunk of wire here, like so, and let's say it is carrying a conventional current to the right. If this was wire, we would be having electrons moving to the left. If this is a nerve cell, we could be having positive potassiums going to the right. Either is possible, so just keep that in mind. But either way, if we're trying to characterize this current, the way to think about this is to imagine that we stand here by some chunk of the wire right here. We're just standing right here with our stopwatch in hand. And we are going to count the amount of charge that goes by in some amount of time, delta t. So in that time, delta t, how much charge have gone through? Whatever charge is sitting here in this length right here. That length would be equal to the drift velocity of our charge carriers times the time that we were running our stopwatch. Okay, so then we can say the current will be equal to the charge that flows past this point over delta t. So how much charge is that? Well, it'll be the number of charges that go past us times the amount of charge over delta t. Now, it's more useful to think about the number density of charge carriers. This will be proportional to the density of the atoms. It'll also depend on the number of valence electrons that are free. In physics, we do this annoying thing where the lowercase thing is often an uppercase thing divided by often a volume or something else like that. So lowercase n is the charge carrier density. Uppercase n is just plain the number of carriers. And V is the volume. So we can write this total number of charges as the charge carrier density times the volume times the amount of charge that each one of these holds over delta t. But what's this volume? This volume is going to be the length here times the area. And this length is equal to the drift velocity times delta t. So we get that our current will be equal to NQA times V drift over delta t times delta t, and those cancel. Now, more often than not, what people do is they prefer to define a thing called the current density, which you would think would be a lowercase I following this, but it's not. It is a J. And it is the current per cross-sectional area in the wire. So this will be NQA A v drift over A, cancel, cancel. It's NQ times the drift velocity. So it depends on the density of charge carriers, how much charge each one carries, and the drift velocity. This is where you get your typical numbers for that the typical drift velocity of an electron is something like 1/10 of a millimeter per second or so. And this comes from just plugging in a typical current, a typical cross-sectional area, and solving it out. Now, what I won't derive, but I will argue must seem reasonable, is that it's also the case that the current density is equal to the conductivity times the electric field strength. It makes sense that the greater the electric field strength in the conductor, the greater the current. We've already seen that. And conductivity is the inverse of resistivity. So the less resistive the material, the faster it's going to flow. So yeah, that all makes perfect sense. So where I do kind of want to finish off here with this video is I just want to introduce Kirchhoff's junction law, or it's also known as his node law. And this is an exact analog in fluids to the equation of continuity. His loop law is an exact analog to Bernoulli's equation. This is an exact analog to continuity. So let's say, just to make something nice and concrete here, that you've got, I don't know, just this, we'll have say 5 wires that are all soldered together in some crazy starfish kind of thing like this. Now let's say that you've got 3 amps flowing in here. You measure 6 amps flowing out there, 4 amps flowing in here, 2 amps flowing out there, and you want to know what's happening here. A way that you can express Kirchhoff's junction law is to say that charge in equals charge out, or else charge piles up until it does. That's just like expressing continuity with fluids. Stuff in equals stuff out, or else stuff piles up until it does. Same kind of deal here. In steady state, what that's going to mean, once our charges have shifted around in order to coax charges to flow through the solder joint here, is that the sum of all the inbound currents has to equal the sum of all the outbound currents. Otherwise, we would be piling charge up at the junction. So if we want to think about our mystery current here, what have we got going inbound that we know about so far? Well, we've got 3 amps plus 4 amps inbound there. Outbound, we've got 6 amps and 2 amps. So this is 8. This is 7 so far. So our mystery current must turn out to be 1 amp, and it must be going inbound. Alrighty, in the next video series we will be doing more with electric circuits, so have a good one and catch you over there.